Hey everybody, today we're going to talk about the sinusoidal nature of simple harmonic motion. Sinusoidal, what does that mean? Well, that means a sine wave or a cosine wave. It's going to look like that when you graph it. And a simple harmonic oscillator, like a mass spring system or a simple pendulum, these will have the same basic mathematical structure as we're going to see. Now, what we're going to talk about is we're going to talk about Hooke's law. We're going to talk about the energy in a mass spring simple harmonic oscillator, and then we're going to compare that to uniform circular motion. And we're going to see that if you have a spring and a mass, and this spring is making this thing oscillate back and forth, that this kind of motion is mathematically linked to uniform circular motion. And we're going to review these ideas first, and then we're going to show that link between circular motion and simple harmonic motion. And we're going to end up with this equation, that the velocity of your oscillator is equal to the maximum possible velocity times the square root of 1 minus x squared, that's our position x, divided by a squared, and a is our amplitude, and we'll define that here in a little bit. And we're also going to develop these equations where the angular frequency is equal to the square root of k over m, where k is the spring constant and m is the mass. And then we're also going to show that the period is equal to 2 pi times the square root of the mass over the spring constant. And the last thing we're going to do is we're going to talk about a simple harmonic oscillator as graphed by x equals a cosine omega t, and that the velocity as a function of time is equal to a omega sine omega t, and then the acceleration is a omega squared cosine omega t, and of course omega here is the omega that we see right here for a mass spring system. So let's get started. Let's take a look at a mass spring system. And of course, these are all idealized systems. There's no frictional losses, there's no noise, no air resistance, nothing like that. So in other words, this thing will pretty much oscillate forever. So this spring has a certain spring constant of k, and remember that's if you change the force on the spring, what change in length of the spring would you get? And so this is in newtons per meter, and this has some mass m in kilograms. And remember Hooke's law. Hooke's law says that the force of a spring is equal to, well, it depends on how much you've stretched it from the equilibrium position, and we're going to call that 0. Here's x equals 0 is our equilibrium position. Now what this means is that the little car here, or our mass, is in equilibrium at this position. That is, there's no net force on it. If I just placed it right here, it would just stay at rest. The spring is applying no force at all. But then if I stretch it out to some position like this, some distance x away, then the force, the spring is going to pull on it with some force. And this force, the spring force, is directly proportional to how much I've stretched it. Now, how much force you get depends on how stiff the spring is. And so we have this spring constant here. And the last thing is, well, this force is a vector, and so is our position is a vector. And so if x is positive, look, if I pull it out like this, like a positive x, the displacement vector is to the right, or the position vector is to the right, but the force vector is to the left, so it's in the opposite direction. And the same is true if it's compressed. If this massive object is over here and the spring is all compressed, the force the spring applies will be to the right, and the displacement will be to the left. So the position and the force are always in opposite directions, and that's what that negative sign means. And this right here is Hooke's law. Okay. Now, if I pull this thing back and release it, it's going to oscillate back and forth like this. And let's say its position of maximum displacement, we're going to call A, and A is for amplitude. And you can also think of it as the maximum x, plus or minus, the maximum position from the equilibrium position. And it can be on this side, this is positive A, and over here would be negative A on the other side. And it's just going to oscillate back there. Okay. Now let's think about this in terms of energy. The mechanical energy, well, if you're way out, if you're at the maximum amplitude away, either on this side or on this side, it doesn't matter. Remember that the mechanical energy, well, mechanical energy is defined to be kinetic energy plus potential energy. Now, what kind of kinetic energy do we have? We have kinetic energy is 1/2 mv squared. And then the gravitational potential energy, the gravitational potential energy is not part of this problem. It's not gaining or losing height, so it doesn't matter. But this is elastic potential energy, and we have an equation for that, 1/2 k x squared. So go back and review energy if you don't remember this equation. Now, let's say when you're at the extremes, when you're out here at the amplitude, for an instant, this little thing here is stopped. It's not moving. It has no kinetic energy, so the kinetic energy is 0. But the elastic potential energy, well, it certainly has it. And it has the maximum possible amount of elastic potential. And in fact, all the mechanical energy is elastic. So that's going to be 1/2 k a squared. Okay, but what if it's in the very middle? Well, if it's at the equilibrium position at x equals 0, well, if x is 0, it has no energy, no elastic potential energy, but it's moving at the maximum velocity, and so so all the energy is kinetic energy, and so that's going to be 1/2 the mass times the maximum possible velocity squared. Okay, so we're going to use all of this. These are when it's at the extremes, and this is in the very center, and this is when you're anywhere in between. The energy is shared between kinetic energy and elastic potential energy. Okay. So we're going to use these ideas right here to show that that this mass spring simple harmonic oscillator will be described by cosine or sine waves called sinusoidal waves. Now, completely different topic here. Let's review circular motion. And so here's a circle, and here's the center of the circle, and I'm going to call this, very important, I'm going to call this the x-axis. So this is circular motion. Okay, and so suppose I have an object that's right here, and it's moving. Okay, and so we're going to remember that velocity is always tangent. I'm trying to draw this tangential to this circle like this. This is going to have some radius. Now, usually we call the radius r, don't we? But for here, we're going to say that the radius is A, capital A. We can call it anything we want. I'm going to call it capital A. Yeah, because we're going to relate that to the amplitude of the simple harmonic oscillator here in a few minutes. Okay, and remember that if this goes around and around and around and around like this, this is v, the speed of this object is a constant, and therefore you can call this the maximum speed, but we're going to call it that, and you'll see why here in a minute, but it's just moving around at a constant velocity. And we're going to say that this thing has been rotated up some angle theta, okay? And, so this thing's just going to move around. Now, what we're going to do is we're going to show that this mass spring oscillation, there is a link between it and this circular motion right here, and so let's do that. And I'm going to do it in 2 different columns here. And this is going to be my simple harmonic motion oscillator, and this is going to be my circular motion. And I'm going to treat these as completely different things, but we're going to end up with the same result. And what that means is that they are mathematically equivalent to each other. So let's get started on the simple harmonic oscillator. So let's start off with the total energy. E equals, let's center this better. The energy equals the kinetic energy plus the potential energy. And so this is going to be 1/2 mv squared plus 1/2 kx squared. And what I'm going to do is I'm going to set that equal to the maximum elastic potential energy, 1/2 k a squared. Okay? So this is when our mass spring system, here I'll just draw a little sketch of it right here. You know, it's just moving back and forth between negative A and positive A. And let's put a position that's kind of somewhere in between 0 and the amplitude, so some value of x. And so it's got some kinetic energy at that location, and it's got some potential energy at that location. And that has to equal to all the potential energy it has when it is at its maximum and it's not moving. All right, so hopefully you got that. Now what I'm going to do is I'm going to solve this for v squared. So if I do that, the 1/2 goes away, and I'm going to divide by m. And so what I get is I get v squared equals, not ready for the equal yet, plus kx squared over m equals ka squared over m. Okay, now I'm going to put this on the other side. V squared equals this thing, k over m times a squared minus k over m times x squared. Okay? Now I'm going to do something kind of funny, and if you were in my class the other day, I really messed this up, and this is where I went wrong. Well, one of the places where I went wrong. I'm going to do a little mathematical trick. I'm going to do something to this. I'm going to multiply it by a squared, which is totally legal as long as I divide by a squared. So in other words, this term right here is not changed by multiplying by a squared divided by a squared. Okay, this is 1. So that will go away, but I don't want it to go away. I'm gonna have it stay, because look what I got. I got a k over m in both terms, and now I've got an a squared in both terms. And so let's factor those out. So v squared equals k over m times a squared. Now what's left here is just 1, right? I factored out the whole thing, so it leaves 1. Minus, now I factored out the k over m, but I didn't factor out the x squared. And I didn't factor out this other a squared, so I got an a squared on the bottom here. Now, look at this right here. This k over m times a squared. remember this, that the maximum potential energy is 1/2 k a squared. 1/2 k a squared. That's our maximum potential energy when I'm out here at either this extreme or this extreme. That has to be equal to the kinetic energy when we're in the very center, 1/2 m v squared. And this is V max. And I'm going to solve for V max squared. So the 1/2 goes away, and I'm going to divide by m. And I get V squared, V max squared, is equal to k a squared over m. But look, that's exactly what that is. So now I'm going to substitute that in, and I'm going to get V squared equals V max squared times 1 minus x squared over a squared. And then the way it's shown in the book is they solve for V. So V, the speed of my mass spring oscillator at any given time is going to be equal to plus or minus. That just means it's either going to the left or to the right, and it's going to do both, right, as it oscillates back and forth, times the square root of 1 minus x squared over a squared. Woohoo! All right. That wasn't so bad, I hope. That's what I was trying to do in class when I totally messed it up. All right. So we have this. We can use that, right? So that we can use this to figure out how fast our simple harmonic oscillator is going in terms of, well, I could just have left km a squared in there, or in terms of the maximum velocity. So that's a useful little equation. Now let's take a look at circular motion. I've already drawn the picture up here, so I'm going to use that picture. And what I want to do, and this is just a little bit of some fancy geometry here, and let's see. This is our maximum. I'll call this V max right here. And what I'm going to do is, if I rotate this up through theta, and this is where our object is located, then I'm going to make a couple of triangles. And here's our position along the x-axis. From here to here is x. Right? From the center out to here, we're going to call this x. This is A. And look at this triangle right here. If this is theta right here, let me erase theta there. So here's theta. And then this right here. Well, look, if here, this is a right triangle, isn't it? From here, here, it's a right triangle. So what is this leg in terms of x and a? Well, use Pythagorean theorem. A squared equals x squared plus this y squared. So what is y squared equal to? It's equal to a squared minus x squared, take the square root. So this leg of this triangle is equal to the square root of a squared minus x squared. Okay? Now, let's take a look at this velocity vector. And you know what? I'm going to zoom in. I hope I remember to zoom back out. Oh, it takes so long to focus. Need a better dot cam. All right. Now, look. Here's this angle theta. Well, you might remember from geometry alternate interior angles, or this is theta here. But this is a 90-degree angle. So this is 90 minus theta. Well, if this angle here is 90 minus theta, that means that this, and this is a right triangle, that means this angle over here is theta. So if this is theta down here, we just went through this little triangle stuff to show that this angle right up here is also theta. Now we're going to use that now to develop a relationship between x and the amplitude and our maximum velocity. So let me zoom back out. Yeah, remember. Okay, so let's take a look at sine theta. Now, these two triangles here and here, they're similar triangles, right? They have the same angles. And so the sine of theta is the opposite leg over the hypotenuse. So this is going to be the square root of a squared minus x squared divided by a. But what, now let's apply the sine theta to this. What is this? Well, this right here, here's what we're going to do. This velocity, we're going to take a look at the x velocity, just the velocity in the x direction. Well, it's the velocity, but see that the angle is up here. So it's the opposite over the hypotenuse. So the opposite is Vx. And then the hypotenuse is the total speed of my object, which we're calling Vmax. Well, let's solve for V. Let's solve for V in the x. So V in the x is equal to a squared minus x squared divided by a times Vmax. Right? It's this times this divided by this. Now let's take a look at this guy right here. I'm going to just do a little algebra trick. And that is I'm going to multiply this, well, here we have an a squared minus x squared, and I'm going to multiply this by a squared divided by a squared all over a. So this doesn't change x squared. I mean, these two cancel out, but I'm not going to cancel out. What I'm going to do is I'm going to factor out this a squared. So this is going to be equal, let's zoom in a little bit. This is equal to the square root of a squared times 1 minus x squared over a squared. Does that make sense? And then we're dividing that by a. Well, what's the square root of a squared? It's a. So Vx is equal to a times the square root of, oh, and what have I left out of here? Vmax. And Vmax over here. Sorry about that. So this is a times 1 minus x squared over a squared divided by a. Oh, that cancels out. All times Vmax. I keep forgetting to do that. So I'll tell you what I'll do. I'll put Vmax first. Vx equals Vmax, the maximum velocity, the velocity of my circular motion, or the speed of my circular motion, times 1 minus our position x squared over a squared. A squared is the radius of our circle. Well, look at this. They are mathematically the same. Okay, we do this a lot in physics. There is nothing I did over here on this side. There's nothing I did over here that had anything to do with the mass spring system over here. And the same is true over here. And yet, when you go through these tricky little math things, you end up with the same thing. This means that an object rotating with constant velocity around here is mathematically, has the same structure as a mass spring system oscillating back and forth. Now, here's what you have to imagine. And I got this diagram from the book. Here's the book. Let's zoom in. Okay, now check this out. So here's a tabletop, and there's some object that's moving around in a constant circle, constant speed, circle around here, uniform circular motion. And you've got your observer right here, and he is looking at it edge on, so that you can't see the circle, you just see basically the x-axis. And as this thing circles around, what he's saying is that it's just oscillating back and forth like this along the x-axis. So what that means is that simple harmonic motion looks like this, which is the projection of circular motion onto a single x-axis. So they are there's a lot of mathematic equivalence between the two. So now why is this a big deal? Well, this means that I can use some of the same mathematics that I used for circles and circular motion, rotational motion, to represent simple harmonic motion. Okay, so now let's, I gotta zoom out. I'm here all by myself, so no one's here to tell me what to do. Let's re-examine circular motion for a little bit. So here's our circle, and here's our x-axis and our y-axis. And here's our object. I'll put it up here again. And it's got some speed, v. Now, and it has some theta like this. And we're going to call this A again. Now, one of the things that we talked about, look, here's what we're doing. We're projecting the motion onto this x-axis. So let's say this was an object. Maybe I had a really bright light up here, and I'm shining that light down here, and I'm seeing a shadow of this. And as this thing moves around in a circle, this guy right here, you know, as this thing moves up like this thing moves down like this, and then they meet here, and then they come across like this. Okay, and so in here is where your simple harmonic motion is. Now, if I were to look at the x position, x is equal to a cosine theta, right? If this is theta. But theta now is changing with time. Theta is moving with a constant angular velocity. So really, theta right here is equal to the angular velocity times time. Remember the kinematic equation? We had delta theta equals omega naught times t plus 1/2 alpha t squared, right? These the kinematic equations, right? For rotational motion. But here we don't have an alpha. We don't have an angular acceleration. It's just uniform circular motion like this. So this goes away, and this omega naught. This is just omega. Okay, and so I can now say that x equals a cosine omega t. Okay. Well, what is the... Oh, okay. Now, I'm going to punt a little bit here, and I'm just going to go to calculus. It can be shown, and take calculus next year, it can be shown that if you take the velocity of this, well, that's the slope, or that's the derivative of x. And so we're going to get negative a omega sine omega t. And then the acceleration equals negative a omega omega squared cosine omega t. And now this has nothing to do with the simple harmonic oscillator yet, but here's what I want you to see. What is this? This is a cosine omega t. Well, what is a cosine omega t equal to? X. So we can say that the acceleration is equal to negative omega squared times x. Now, you don't really have to remember this that well. I'm not going to use, I'm just kind of deriving something here. Well, look at Hooke's law. Hooke's law says the force of the spring is equal to negative kx. Well, for a mass spring system, the force of the spring is the net force. So this is going to be equal to ma equals negative kx. And so A is equal to negative k over m times x. Well, look, this has the same mathematical structure. And so what we can say is that omega squared is equal to k over m. And what does that mean? Well, that means that the angular frequency, the frequency at which this mass spring system will oscillate, how many radians per second it will go through, is equal to the square root of k over m. And this is one of our basic equations that we wanted to show. Now, the book does it a little bit differently. Read through that. Using this idea right here is just a lot faster, and this lecture's already too long. Now, we also learned when we were doing rotational motion that period is equal to 2 pi over our angular velocity. Now, what is period? The period is the time to make one circle. But if you have rotational motion and you go through one circle, what has x done? Well, it's gone through one complete oscillation. So the period of circular motion is the same as the period of simple harmonic motion, one complete oscillation. Well, this is equal to 2 pi over the square root of k over m. And this gives me t equals, stay on screen, t equals 2 pi times the square root of m over k. Okay. Now, last thing, if you look at these equations here, what is our maximum possible position away? Well, we call that the amplitude. But I mean, cosine omega t, what's the biggest it can be? Well, the biggest cosine, well, when omega t is 0, when t is equal to 0, we're starting at this position, and that's our maximum amplitude, right? Because cosine of 0 is 1, so cosine omega t is 1. So x max equals a, plus or minus. And then what about v? Well, the maximum velocity is equal to a omega. Now, we did this with circular motion, right? We did this with, we said the maximum velocity is equal to, this would be the radius of the circle, and this would be the angular velocity. And then our acceleration, the x component really of that acceleration is equal, and this is plus or minus, it's plus or minus a omega squared. And this gives you the direction of the maximum acceleration that you're going to get on that. And really, you can get this maximum acceleration from Hooke's law directly, right? I mean, when you're at the maximum acceleration, here's our maximum acceleration will be when x is at its maximum. and x is at its maximum when you have the amplitude, and this is, we said this is omega squared right here. So it all kind of fits. So this is kind of mathematically rigorous and difficult, and because, I mean, doing this, hopping down here to here, it really, you need calculus to do it, but I want you to see it. And then, where is it? Oh, no, sit down. You know what time it is. All right. Here you see a graph that really shows here's our cosine wave. And if you take the slope of this, zero slope, and then you just take the slope of this and follow it around, you get this graph. And then if you take the slope of this, right, because acceleration is the slope of velocity, you get this graph. And notice that this graph is a cosine wave. This graph is a negative cosine wave with a different amplitude now, km times a, k over m times a. But this really shows the relationship that I just kind of showed with equations. This is a graph. All right. So I think this is enough for now. There's a lot going on here. What do you really need to know? You need to know that a simple harmonic oscillator is mathematically very similar to circular motion. We proved that by showing that the velocity, the x component of the velocity of this is mathematically identical to simple harmonic motion. Okay, so therefore we can use the mathematics of circular motion to analyze simple harmonic motion. The angular frequency, that is in radians per second, is equal to the square root of k over m. And then the period is equal to 2 pi times the square root of m over k. And you should be able to get everything you need from that. Well, hey, if you've written this down, if you have questions and you're watching this online, obviously, write your questions down, put them on Post-it notes, and then bring them to class. Okay, that is all.